Okay, good evening everyone. I hope you are fine and comfortable to start now. I think there are no more people joining us. So, first of all, before I begin the talk, I would like to thank Alex and for helping me organize this event, and Justin and JetBrains for sponsoring us with the pizzas and the drinks today. So, let me first begin with a short introduction about myself. I'm a master's student at TUM and with a major focus on artificial intelligence. I've applied a wide range of machine learning algorithms across the medical imaging, robotics and security domain. And in particular, I'm interested in applying statistical relational learning, natural language understanding, and some advanced machine learning topics in other domains as well. And you can reach me at any one of these mediums, as I'm always on the lookout for collaborating on novel and challenging projects. So the agenda for today's talk is I start off with introducing how this topic fits into the different machine learning paradigms. Next up is some basics or concepts or theoretical background. Then what are the state-of-the-art tools and current or active research going on in this field. Then I talk also about the industry applications or use case scenarios. I think this would be of interest for many people here who are coming from an industry background. And in particular, I would touch base upon one such application scenario from the robotics domain. And finally, to conclude this talk with what are the applications or how this field is emerging, and some references and additional reading material as well. So let's look at the 5 different machine learning paradigms, and each of which is inspired by a different field. So the first one is the so-called the connectionist, as they are called, led by Geoffrey Hinton. I guess not many people know about him. He's like one of the founding fathers of deep learning from Google and the University of Toronto. So they believe that it's the brain that does all the complex calculations. So why not mimic the brain? So this field takes inspiration from neuroscience. On the other hand, there's another group of people called the evolutionists, which think it's not the brain, but something that was precedent to the brain, evolution, the process of evolution itself. So they are led by John Holland from the University of Michigan, and they believe that the fittest ones stay in the race and they're using this to program 3D printers for future robots. Another school of thought which believes that it's not the about to, but analogy that acts as the core of cognition, and they are led by Douglas Hofstadter, who's a famous American writer and published a famous book on this. Symbolists like Stephen Muggleton from the Imperial College of London believe that rules and deductive reasoning is the master algorithm to build anything, and then they have this robot scientist called Adam at the University of Manchester. And lastly, there's another, or the last field which is relevant to statistics and logic, and this is what is the focal interest today. Bayesians, as they are called, and this field got prominence after 2011 when Julia Pearl from the University of California, Los Angeles published his work on Bayesian networks. So they are like the most fanatical of the lot. They believe that everything can be represented by a Bayes theorem, and they can be, the hypothesis which they create can be updated with new evidence. So regarding some background, we always often assume that any data is independent and identically distributed. However, real world data is not. And SRL, or Statistical Relational Learning, basically tries to attempt and represent, model and learn in the relational domain. And there are four major models in SRL. They are probabilistic relational models, Markov Logic Networks, which is what we are going to discuss, I'm going to discuss in detail today. Then relational dependency networks and Bayesian logic programs. So what exactly is a Markov logic network? It is a powerful framework combining statistics, that is Markov Random Fields, and logical reasoning, that is first order logic. And some of the famous names or bigwigs in academia who are doing like active research include Professor Pedro Dominguez. He's from the University of Washington, and it was his work in 2006 where he and another guy called Richardson, they published the paper on MLN. Then we have this Professor Luc Deret from the University of Leuven in Belgium, and they introduced a tool called ProbLog. Sorry, I missed this. The research group of Pedro introduced the first tool called Alchemy. Currently, Stanford has this Hazy project group, which developed a lot of tools called Tuffy, Felix, and so on, and I would be discussing this a bit later. So coming close to Munich, actually, we had Professor Michael Beetz from TU Munich, but now he and his whole team have moved to TU Bremen, the AI department there, and they also created a tool called ProbCog. Actively or presently, right now, only as far as I know, Professor Volker Press from LMU and Matthias Nichols at TU Munich are the ones who are doing some active research in this field. Yeah. This is Professor Michael Beetz. Okay, so some background about before we go into the advanced topics. So what is actually a probabilistic graphical model? The definition says a probabilistic graphical model encodes a joint or a conditional probability distribution such that given some observations we are provided with a full probability distribution over all the possible solutions. So basically we try to encode relationships between a set of random variables, and how do we do that is by using a graph. And this graph can either be a directed or a undirected graph. So what is a Markov blanket? It is a directed or cyclic graph. It is a Bayesian network where the nodes are dependent only on its, so if I use this example, so this node A is dependent on its parent and also parents of its descendants. So for this node, the Markov blanket is represented by this circle. So this is actually the only knowledge that is needed to predict that node A. Next is Markov Random Field. It is another undirected graphical model where each node satisfies the local Markovian property that is of conditional independence. So if we look at this figure, the black node is conditionally independent to any white node given the neighbors, that is the gray nodes. Same with this one. So basically connecting it with the previous slide Markov blanket for this node would be simply its neighbor. So now coming to the main topic, that is MLN, what is the intuition behind it? So we know that probability. Sorry?
May I ask a question?
Yeah.
Can you go back to the previous slide? So what's the difference between the Markov random field and the Markov chain? The thing is that these nodes are random variables, right?
Yeah.
So the black one depends on the gray ones.
No, I mean the main thing is this black one is conditionally independent of this if we are given this information.
Those are given.
These are the only information that is required. So for this node, only the adjacent nodes are of importance to calculate or evaluate this node.
Okay.
So like a Markov chain would be not just in one dimension. Like for example, you can have like here you have like 4 directions. Like in a chain you are just having the current state depending on the previous, but here you're having like 4.
Mm-hmm.
It can be even more. Like this is just an example.
Okay.
Yeah.
Thanks.
Yeah. No problem. So the intuition behind Markov Logic Network is first of all, we know that probability handles uncertainty, whereas logic handles complexity. So what if you bring both of them together? So we get kind of best of both worlds. So MLN basically does this. It tries to bring or combine logic and probability together. So how does MLN look like? It has a set of pairs of formulas. These formulas are represented in first order logic, and along with that we have weights, which is a real number, and then this is represented by this where W is the weight and F is the formula. And basically MLN provides a template to ground a Markov network. So the definition goes by this. It's a log linear model wherein the probability of a world X is given by this formula, where it is a weighted sum over all the true groundings of the formula I, and of course under an exponential, and it's divided by Z, which is called the partition function. This is required to normalize these values to come between 0 and 1, so as to have a probability. Yeah.
I'm sorry to interrupt
Yeah,
again.
sure.
Sorry. So how? Oops.
Okay.
What is the grounding of a formula? Is a choice of values?
Yeah, I would come to that in the next few slides.
Okay.
So grounding is basically when you replace the formula with true or ground predicates values. I would come to that. Maybe if it's not clear, I can come back in the next few slides. So how does a MLN template look like? It has like 4 major components. So the first one is the predicates or the rules. So we need to first of all specify what we want to learn, like what is the relationship. So that is expressed in first order logic. First order logic, as everyone knows, comprises of and, or, implication, and so on. Then we have evidence, which is what is the ground predicates or the known facts, which we already know. Then we do these two processes, that is weight learning and inference. Weight learning is basically trying to discover the importance of relationships based on grounded evidence, and inference is to query the relations given partial evidence. To infer a probabilistic estimate of the world. So more on these two in the next few slides. So weight learning is basically a log odds probability between a world F where it is false and where it is true, and a world where it is false, given other things being equal. So it's represented by this formula. So it essentially captures the marginal distribution of the corresponding predicate. So we have some rules, and the weight will basically try to capture what is the distribution. And each formula has a weight, and this weight reflects how strong that constraint is. So here comes the grounding part. So we have the formulas, and when we replace for each formula in the predicate with its constant values from its domain, we get a grounded network. So that is what is grounding. So let's look at this with the help of an example. So if you look at the center, this is my file with the predicates. So in this example, I hope it's clear. So we have this 2 predicates which we want to model or learn about. So the first one is N subject, which means a noun subject. This is an NLP based example. So which consists of 2 parameters, which is a verb and a subject. So basically this wants to learn the relationship between a subject and a verb. And similarly we have a direct object represented by D object, which tries to learn a relationship between a verb and an object. So these are my 2 predicates, and I have used a first order logic to combine these 2 predicates. The plus here indicates like I want to learn for all the subjects and all the verbs. So this is my rule, and these are my predicates. And given some evidence, like this file is my training data. So I have occurrences of D objects. So I know that apple can be eaten. Same, maybe apple can be thrown as well, and so on. A man eats. So these are my ground values or true values. So if I supply this training and do weight learning on this using this set of formulas, this is just a sample example from one of the tools Alchemy. So I get what we call as the weights. The thing highlights the weight, and if you see here, instead of this formula, we have replaced every occurrence of the verb with the corresponding verbs from the training phase and corresponding nouns or objects from the training. So we get like a grounded value, and we also get the weight associated with it. So this weight signifies how strong this particular formula or constraint is.
So this isn't normalized in any way?
Yeah, this is not normalized still.
Not?
No. This is just like the numbers can be real numbers with negative or positive. It need not have like between 0 and 1.
Okay.
So this is like the first phase of this whole framework. We do inference after that. In that we have normalization. So the next part is after doing the weight learning, we know how strong the constraint is. We try to do or estimate the probability distribution encoded by the graphical model given some data or observation. So the two major inferences which we do generally is like map and marginal. In map inference, we find the most likely state of the world given the evidence. So it can be represented by this formula, where we do a argmax over this, where y is the query and x is the evidence. And this essentially is equivalent to doing the weighted sum over all the true groundings of the formula. In marginal inference, instead of finding the most likely state, we directly compute the conditional probability of the query predicates given some evidence. And there are in fact more advanced inference algorithms like loopy belief, walksat, MCSat, and so on. So let's look at the same example which we did weight learning on. So we had this weight learning file wherein for each rule we had the weights which we learned. So then on this weight learning file we can provide some partial evidence or maybe no evidence with or without evidence. We can query for each predicate and get a marginal inference value. So for example, here we are just querying on the n subset values to get for each possible combination the probability. So the idea is like when we do the whole process, if there are more occurrences of, for example, man and cut, then we do the whole process, this would be assigned like a higher probability. So given enough data, when we do this whole process, we get a closer estimate to the real world. So this is what we are trying to do in this whole statistical relational learning part. So this is with the inference. Now I would like to talk about the current tools or what is the active research going on in this field. So I've assorted a list of all different tools here, and also along with the tools I've just tried to, because there are a lot of them, so I've just tried to highlight the main points or the main features of each of them or what are the problems in each of them. So bugs and PropLog were like the first ones before MLN, so they didn't have this relational learning part in the bug, and then they used some other compiler. PropLog, instead of using first order logic, used horn clauses, and there was no weight learning features. So the file which you see here, you had to manually provide the constraints here, so you couldn't like learn it. Then this is the tool developed by Professor Michel Beach from TU Munich. So it not only covers MLN but other statistical relational learning frameworks like models like BLB and etc. And now it has a user interface as well. The Beast has a shell which also allows you to analyze and inspect the model feature weights. Alchemy, perhaps the first order probabilistic logic tool with both weight learning and inference from Professor Pedro Dominguez and his team. Rocket is again from the University of Mannheim. It has an online and a REST-based interface, and the formulas can only be represented in conjunctive normal form, that is and or. And lastly, we have this tool called Logical MRF, which is Scala based, and it has this feature to do difference between the Markov Random network files. That is, we can compare two different hypotheses as well. So if you are learning with some evidence and with more evidence, you can compare what is the result or what is the way to learn here. So talking about the active research in this field, this group from Stanford, Hazy Project, it leads the way. So these are some of the tools which they developed over the years. So Tuffy, Felix, Elementary, Deep Dive, and many more. So let's look at how and why these tools got transitioned. First of all, of course, due to some additional functionality and missing some problems in the previous one. So as I highlighted earlier, this was not from this group, but this was the precursor to doing all the research in this field. So the first tool, Alchemy, did both wave learning and statistical inference, but it was slow and memory intensive. So they wanted to achieve scalability, so they came up with Tuffy, which uses a relational database management system to do the scaling up. Then they came up with Felix, which allows for large scale inference, but again it didn't have this weight learning feature. So then they came up with another tool called Inference, which is current state of art and uses secondary storage also for scaling up things. So how does this scalability come into picture is, if you look at the tool, the first tool just used like global files for storage. Then they came up with the relational learning, relational database called Postgres for Tuffy. And in Felix they used Greek learn database along with some Apache Manlib incubating stuff with, and all packaged into a virtual machine itself. So and then they are also trying to use now in the elementary and other models Hadoop based or distributed based systems. So the transition is from like local file to database to distributed stuff of map reduce. So this has helped to achieve the scalability aspect. Finally, the last part or wherein I touch base on some of the applications from industry and one such application scenario. So the applications of MLN are manifold. They range from doing entity recognition, web mining, link prediction, and so on. So a famous problem from social network analysis called the friends of smokers can also be done using this. And of course, you can use it for NLP, robot mapping, and so on. So what are the industries which are applying or using this MLN-based framework? So the first one is SoftPlan. This is based out of Ingolstadt, close to Munich, and they are using MLN. They actually used it last year for IT risk assessment. More on this on the next slide. Then this company called Scaled Inference is based out of California in the US. It's a startup in the downtown area of Palo Alto, and then they are like doing state-of-the-art work in large-scale inference, and they want to build an autonomous and distributed system just to mine and collect web-scale data. And lastly, there's one more company which I know. Again, these are like to the best of my knowledge. Cambridge Human is a UK-based startup, and they are currently working on assisting the upper management based on the risk profiles or the sensitive roles of their employees, and they have access to psychological result data which they make use of. And currently this company has got intellectual property rights, and they are targeting the aviation vertical. And in fact there would be like many more. So there are like more use cases or actual use cases of MLN in the industry. And by the way, I'm not getting paid by any one of these to do a advert here. So yeah. So let's look at how SoftPlan used MLN for the validation of IT risk assessments. So they use first of all this MLN tool for detecting anomalies, and then they use this rocket syntax. This was like one of the tools which I introduced in the previous slides. So let's look at what is the predicates they wanted to learn. So this is the predicate. So they wanted to learn how a threat endangers the infrastructure, and the next one was like whether the infrastructure becomes offline because of that, and whether the infrastructure depends on another one, and what are the domain values of infrastructure. So the infrastructure is server and router. Similarly, the threat can be a virus or a temperature. And based on these predicates, they use first order logic to construct a formula where, if you read this means for every thread and infrastructure, if the thread endangers the infrastructure goes offline, and then you have a weight which is learned for this. And similarly, you have another rule. So based on this set of rules and this training file, or the ground predicates, which we call the evidence, which has all the known facts. So we know that a virus endangers a server and also a router, also temperature and so on. And then if we do this, so we get like a grounded network, where each variable here, T and I, is replaced by all the possible combinations, and then we learn a weight based on it. And then this is the weight learning part, and then we do inference to get like real estimate of, yes, this particular is very high, so maybe we need to take care of this, or this is a potential risk. So this is how they use. More can be referenced from this paper, which I highlighted at the end as well. Yeah. So the last part of this talk will touch base upon one such application scenario from the robotics domain. I guess I will take 10 more minutes, so please bear with me. So this work is called Prior Affordance Understanding with Relational Learning for Human Safe Action Planning. Quite a big name. So this paper actually stemmed from an academic work which I was doing under my co-author, who was my supervisor. And we presented this work at the ICRA workshop recently in May in Stockholm. The workshop was called AI for Long-Term Autonomy. So first of all, what is the motivation behind this? So cognitive robots still lack what we call as the common sense knowledge, and affordances encode relationships. I would like to highlight relation here. Between actions and objects. So basically, it gives us an understanding of how an object can be acted upon. But the current state of art, the affordances which we obtain, is obtained by sensory motor exploration with reinforcement learning, and we cannot use it as an initiation. So if you look at this figure, for example, if a apple is placed in front of a robot, it doesn't know what it can do with the apple. So the current state of art is like to give some learning, which is with reinforcement learning. But as I said, it cannot be used during initiation. So we learn some task, we learn it through text, and then the robot gets to know, yes, an apple can be cut, an apple can be picked, and so on. So in this work, we are providing both an initial and a safe estimate of task. So the goal of the whole project could be depicted by this figure. So if you look at the top left, we have what we call as training, wherein we do some scraping of text or crawling of text from wikihow.com. So the text reads like this: clean the floor as a final step, follow up dusting by cleaning the floor. So using this text, we do some grammar dependency extraction, and we get different relations. So we get like a relation between the verb cleaning and the object floor called the object, and similarly we also get some other relations. And then once we get these relations, we can pass it to a relational learning framework where we have our predicates and the rules, and to learn the weights. And after we have learned the weights based on these ground evidence, we can do a map inference to predict, and at the end the whole goal is to give the robot some cognizance about what kind of activities or tasks it can do. So the technologies which we used in this project were Stanford type dependencies. So what are they? They just provide a straightforward description of grammatical relations. So in particular, we selected only N subject and D object because we just wanted to know whether the object is active or passive. And these two relations are enough to represent that. Because there are other relations like, for example, auxiliary verbs and so on, but this is enough and had low passing error rates. And of course MLN, which I've talked up in detail up to now. And in particular, I would like to highlight Tuffy because we wanted to scale this, so we used Tuffy, which used this RDBMS. So how does the training phase look like? We did web crawling, but we needed to select a corpora. A corpora is what kind of text or what should be our domain. So we could have simply selected Wikidump, but Wiki has a lot of figurative text and that doesn't suit our requirements. So we wanted technical text, which is a kind of a user manual, like IKEA manual. You get how to do daily tasks. So we came across WikiHow, which is basically a user manual like text on daily household tasks, which we scraped to extract the text. Moreover, we did some pre-processing. That is, after extracting the text, we wanted to make sure that it is easier to compare them. So we lemmatized the inflected word forms to its move. So, for example, the words moving, moves will all map to the word move. So this facilitates comparison. And then after doing this, we did the second part of the training phase was doing this statistical relational learning, wherein we had this predicates. So for us, the predicate was just D object and N subject, wherein we wanted to learn for every verb what are the different objects, and similarly for every verb what are the different subjects. And then at the end, we did inference on top of it using a specific advanced MC-SAT algorithm. So the whole system pipeline looks like this. So we start off with the training phase with doing some web crawling on the internet, that is Wikidump, to extract some technical text. Using this text, we did some parsing on top of it to extract all different grammar dependencies. And out of it, we were only interested in the verb, subject, and object pairs, so we only extracted those in subject and the object. And then pass it to this ability modality processing, which is a statistical relational learning MLN framework, which gives us the input probability of N subject and D object pairs. And then we have just a simple checker which decides whether if for that possible noun or with the verb, if the probability is more, then it is more likely to be an object, so then it's a passive, and on the other hand it can be active. And we compare this with the test data which we obtained from CAD 120, which has 10 high-level affordances of daily human activities like picking, moving, cleaning, and so on. And then we compare our approach. So these are the evaluation results. So we try to plot the percentage values of the correctly classified, misclassified, and out of vocabulary text which we had, and on the x-axis we have the number of words. So basically we are trying to model or learn what are the object passivity rates based on the number of WikiHow words. So at the start, you can see it has a very high out of vocabulary rate, and also this the correctly classified is also less. So then we decided to scale or increase the data, and that is where we made use of Tuffy to scale this up. So then as we scale to more and more words, we get the misclassified rate to 0, and also the out of vocabulary text also drops down, and also we reach almost a maximum for the correctly classified. So basically this aligns also with our intuition that given more number of words or more text, we arrive or we derive more knowledge out of it, and we can correctly classify whether an object is active or passive. So the relationship, that is whether it is active or passive. And finally, we evaluated it against the ground truth of this CAT 120 data set that I highlighted earlier. So with this small subset of data itself, we got like optimal convergence rates and also acceptable classification rate. So we have tried to verify a proof of concept that we do not attribute something which is insecure, something that is insecure as safe or nor the inverse. So these are the references which I would like to highlight. So this is the paper introduced by Pedro Dominguez in the year 2006. It has like the whole basics of this Markov Logic Network. This is the paper which I presented a few months back, and this is the intuition or the idea from where we did this. And this is the work from industry, that is the soft plant IT validation assessment, IT risk assessment, which I talked about. If you're interested, maybe you can read this as well. So, yeah.
So what are the prerequisites to reading each of those papers?
Prerequisites are a bit of like the background thing which I introduced at the start. So you should know like maybe what is a MRF or Markov Random Fields or some stuff like that. So this paper is like maybe like a Bible or something. It has like it is the base which was built on top of it. So I would recommend maybe this paper, or maybe actually I have some more additional references which might help you. So first of all, this is an emerging field, and especially the scalability aspect of it is helping it emerge even more. So this field was like limited at the start with just files and stuff, but now with active research, we can really scale it to real world data, because real world data is not limited to just like some research concepts or just files. So it is hard, so maybe it is better to dig deep now. And perhaps you can use it to model relations in your industry projects, as I highlighted like 2-3 use cases which I came across. Maybe you also could identify a use case in your project or in your company. So there's a TEDx video by Pedro, which from the University of Washington, which is called "The Quest for the Master Algorithm." It is what inspired me. The first few slides are based on this video. Then you have this Hazy project webpage. I would strongly recommend you to go over this page, because it has like not just the tools and stuff, but also good documentation and tutorials as well. And also the Alchemy webpage from Pedro's group, it has also some tutorials. So maybe that is also a good starting point, because it not just covers like the theory or the mathematical stuff, but more application oriented stuff. So maybe someone can relate it a bit more. And if you're interested to dig deep perhaps in my application, so there's this code and there are some evaluation results which are put in this link. Of course, I would also share the presentation slides with you. And I wrote a small blog on the whole experience at the conference, so if you are interested, maybe you can check this as well. So with this, I'm almost done from my side. If you have any questions.
Can you put the last slide on again?
Yeah, sure.
Thank you.
Yeah.
I would have a question about
Yeah, sure.
whether there's any work on landing the formulas you made. I mean, the predicates you as a given. You have this
Yeah,
predicate.
you define it yourself. Like,
But the formulas, is there any work on learning them somehow? Because there are potentially infinitely many.
Yeah.
And maybe
so basically, you have to model it. Like, there's no like. I mean, whatever formula you model, the weights would highlight how strong that constraint is. So the formula you have to model.
Yeah.
There's no what do you call it? The formulas cannot be learned on its own.
Yeah.
The weights for it, or
I guess you would have your domain experts who would come up with the formulas and like confidence level, and then you can test them.
Yeah.
That's what I understand.
Yeah.
so for example, here they were sure like they wanted to do like this detect an anomaly. So they had this kind of formula where they wanted to check what kind of thread brings the infrastructure offline. So this again, as he highlighted, maybe the domain experts would kind of comment here, like what kind.
So the maximum posteriori is equivalent to maximizing. What does the second formula mean?
Like this means like we have the I stands for all the different formulas, and we have the grounded the ones which we did. If you see the previous slide, like this one, we have like all the grounded version and then the weights. So it's like just doing like a sum or
Okay. Yeah.
so
you learn the weights, which are those pink weights.
Yeah.
Okay.
yeah. Any more questions? Any comments or any feedback or anything? Was it too fast or was it too dense? Or maybe, I don't know. I tried to, because this is like a very vast topic, I tried to cover it like from, yeah, please.
So with your final example of mining some language corpus, or how do you call it? What's the benefit of this method compared to regular statistical analysis? Well, here you have like all the data on how the different words can be used together in several contexts. So basically, you are not trying to predict any words. You are not trying to predict any new combinations of words, from my understanding. So basically, this is just some fancy method to analyze the probability of meeting two words together. So in a certain relation in a text, or is it much more, something more?
So, for example, in this work, like the current, like what was being done was like they used like relational learning, but we wanted to have like if you extract text from say wikihow.com, you have text which has been like the instructions are for humans, like humans know like. If you want to, for example, bake a cake, you would first put it in the oven, then maybe raise the temperature and so on. So we can use these kind of text to model the actions of a robot. So
yes.
The text aspect which we use here was not to come up with something new, but kind of like to mimic what a human does, but using text.
Yeah. Okay. So there is some way to combine those. Those sets of actions into something meaningful.
Yeah.
Because on your graph, you just showed the accuracy of predicting that human, I don't know, are drawing objects.
Yeah. So
a lot, but it doesn't help. I don't know, to teach a robot to play basketball, because it's much complex relation.
Yes. So the main goal is to make it learn like the thing which you are highlighting. But in this work, we just highlighted whether the object is like active or passive, whether it can be like pickable, like whether it's pickable, or it can be like acted upon, like whether it's a subject or an object.
Yeah.
So in this context, we just limited ourselves to just deciding what the object can, like whether it is active or passive.
So have you done any comparison to like regular statistics? Because you can just for each pair you have a probability of having this pair in your relationship set, and that's also I don't know.
But
by the number of occurrences of such actions.
Yeah, so the main idea is like as we increase the number of words or the links, like we get like closer to what is like being modeled in like reality. Like we get to know like if you see the graph. So if we increase the number of links or the words, like this is like close to 30,000 words, we get like more close to what is happening in real. Like so then we model like more words which are closer to what it's there in the reality.
Yeah, well, so if you take the whole WikiHow,
Yeah, then
And
maybe even more. Then
calculate
if
the
you maybe
probabilities.
reach 200, yeah. So-
And then you just take the whole WikiHow and calculate the probabilities with regular methods.
Yeah.
Would it be like better or worse applicable to some other? So, for example, if you calculate probability on your test set,